So I would like to invite our first keynote, Dr. Amory Lovins, to the stage, and he has some excellent slides that he is going to share, right? You promise? Yep. Good. Please welcome Dr. Amory Lovins.
Thank you very much. For this opportunity to remind you about how to design for radical energy efficiency. Similar methods, by the way, can also save water, metals, and other resources. Around 1975, our government and industry all said that the energy needed to make $1 of GDP couldn't go down. A year later, I heretically suggested it could drop 72% in 50 years. So far, it's dropped 58% in 43 years. But just the innovations already added by 2010 can save another threefold, twice what I originally thought, and at a third the real cost. Today, though, that's looking conservative because optimizing buildings, vehicles, and factories as whole system, not as piles of parts, can often make very big energy savings, cost less than small or no savings, turning diminishing returns into increasing returns. Now, economic geologists know that a mineral's reserves, the identified deposits profitably extractable with current technology and price, are only a small part of the resource base. Most energy analysts also narrowly define reserves of energy efficiency, like the bright green zone in these mineral resource definitions. But the actual energy efficiency reserves are several-fold larger than are now typically recognized or captured. The missing majority is hiding in plain view, exploitable by integrative design, as I'll explain. But this geological analogy breaks down on cost. Ore bodies are finite assemblages of atoms, while energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. That's documented in a new peer-reviewed paper called How Big is the Energy Efficiency Resource? You can just search on that title. Its evidence shows that unlike oil or copper, most new energy efficiency reserves actually cost less than current production because they come not from adding more or fancier widgets, but from using fewer and simpler widgets, but more artfully chosen, combined, timed, and sequenced. So how do we do this magic? Let me start with a little exercise. One of my early mentors, the inventor Edwin H, said, "Don't undertake a project unless it is manifestly important and nearly impossible." He also said, "The people who seem to have had a new idea have often just stopped having an old idea." Asian tradition tells us to the same thing, to seek original mind, beginner's mind, child mind, to open ourselves to new ideas by shedding our assumptions and preconceptions. So in that spirit, for decades, textbooks on creative thinking have posed this problem as find the solution that connects these 9 dots with just 4 lines without lifting your pen from the paper. So you're supposed to try 1, 2, 3, 4, oops, 5, that doesn't work, 1, 2, that doesn't work. And then you're supposed to think outside the box, which is where that expression comes from. But one day a student startled her professor by saying she had solved this problem in just 3 lines. How do you do 3? 4 was hard enough. Dots are infinitely small. Actually, wait a minute, these are rather plump dots, and you don't actually have to go through the middle of them. So if your paper's wide enough, you can do that. So the students then started to feel liberated, and they started to solve this problem in 1 line. Here are a few of their many solutions. If you're Japanese, you might think of the origami solution. Fold up the paper. If you're a geographer, you might use a very long line. If you're a tool-using critter, a mechanical engineer, you might take a tool called scissors and cut out the dots and impale them. Or if you're a statistician, you can crumple up the paper, and if you stab it over and over again enough times with a pencil, eventually you'll go through all 9 dots at the same instant. The solution I like best came from a 9-year-old girl who said, "You didn't say it had to be a thin line, so I used a really thick line." So as the late great Paul McCready said, this tyranny of the word the, find the solution with 4 lines, put us back in the box and kept us from being properly creative and coming up with more elegantly frugal solutions. So with beginner's mind, never having built a house before and therefore not knowing what was impossible, a third of a century ago I did the conceptual and energy design of the owner-builder house where my wife Judy and I live on the western slope at 7,100 feet. And temperatures there used to go as low as minus 47 F. We once had 39 days of continuous midwinter cloud. But our house does no combustion. That's so 20th century. Super insulation, ventilation, heat recovery, super windows from Boulder that insulate like 16 to 22 sheets of glass, but look like 2, cost less than 3. All that stuff made it 99% passive solar heated, 1% active solar, and eliminating the heating system more than paid up front for the efficiencies that eliminated the heating system. That is, construction cost went down slightly. And then saving also about 90% of electricity and 99% of water heating energy and half the water, all paid for itself in 10 months. Now, the central atrium seen here in a February snowstorm has so far produced 75 passive solar banana crops. And without needing to look like this, our house helped inspire over 160,000 European passive buildings that, like ours, don't need heat and have roughly normal construction cost. Integrative design gives many benefits from each expenditure. So the white arch holding up the middle of the house, it's in the top center picture, has 12 functions, but it has only one cost. Our integrative design to retrofit the Empire State Building saved 38% of its energy with a 3-year payback. I'll tell you how in a minute. 3 years later, our cost-effective Denver retrofit saved 70%, making the half-century-old Byron Rogers Federal Complex more efficient than what was then the best new U.S. office at NREL, and that in turn is less than half as efficient as our own net positive no mechanicals office in Basalt. Now there's a Bavarian building using 3/5 less energy than ours. And yet these technologies all existed over a decade ago. What mainly improved, doubling the best efficiencies in 5 years, is not technology so much as design, the way we choose and combine our technologies. Now, our Empire State Building retrofit remanufactured all 6,514 windows on site into super windows that pass light but block heat. And that plus better lights and office equipment and so on cut the maximum cooling load by 1/3. Then renovating smaller chillers instead of adding bigger chillers cut capital cost by $17 million, paying for most of the other improvements and paying back in 3 years or less than 1 year if we had counted the non-energy benefits to the owner or the tenants. A major energy service company, by the way, had also offered a 3-year payback, but with disintegrated design, saving only 1/6 as much energy. The Intergovernmental Panel on Climate Change reported 5 years ago that for diverse building types and climates, the best European new builds on the left and retrofits on the right are saving up to 90% or more of the energy without raising the cost per unit of saved energy. The better projects are all highly cost effective, and the big vertical cost scatter simply shows the business opportunity to conform inferior practice to best practice. Most climate models assume from economic theory that such big savings must have steeply rising costs, but I prefer data to theory. Timing matters too. In a big glass office tower, super windows plus efficient lights and equipment and such can shrink mechanical loads and systems by 4-fold, more than paying up front for the efficiencies that shrank them. A 4-fold efficiency gain in this old Chicago building could thus pay back in about -5 months. That is cheaper than the routine 20-year renovation you have to do anyway that saves nothing. if you coordinate that deep retrofit with the routine renewal of the curtain wall facade. Deep retrofits of all our big buildings are going to take decades, so we may as well right-time them to make the savings much bigger and cheaper. Go to retrofitdepot.org for portfolio management tools to help you do that. Now, what about our biggest oil burner, automobiles? Well, the propulsion system or powertrain loses 4/5 of the fuel energy before it gets to the wheels. But our savings should start at the other end of the problem. Just 1/5 of a modern car's fuel energy reaches the wheels and moves the car. Of that tractive load, nearly half heats the air that the car pushes aside. Most of the rest heats the tires and road, and only the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But 19/20ths of the mass you're accelerating is the heavy steel car. Only 1/20th is the driver. So just 1/20th of that 6% or 0.3% of the fuel energy actually moves the driver. Not very gratifying after 1 1/3 centuries of devoted engineering effort. Moreover, both the acceleration and the rolling resistance depend on mass, which therefore causes most of the tractive load. Reducing losses in powertrain, where the automakers tend to concentrate, is harder than reducing tractive load, and it's also less rewarding because saving 1 unit of energy in the powertrain saves only 1 unit of fuel in the tank, whereas saving 1 unit of energy at the wheels avoids 4 or 5 units of losses getting energy to the wheels and therefore leverages 5 or 6 units of fuel savings at the tank. Thus, we should first reduce tractive load, then improve the powertrain, which then shrinks for the same acceleration because there's less mass. That saves more mass and also saves capital cost to help pay for the lightweighting. How light can we make an auto without compromising crash safety? Well, using ultra-strong carbon fiber composites, at least 2/3 lighter. How do you do that? Well, a 787 Dreamliner is half carbon fiber composites by weight, but automaking needs about 1,000 times higher volume and lower cost than aerospace. That's a big gap. But in the early 90s, I met Dave Taggart at the Lockheed Martin Skunk Works. There he had led the clean sheet design of a 95% carbon advanced tactical fighter airframe that was 1/3 lighter but 2/3 cheaper than the 72% metal base model. That was too radical for the Joint Strike Fighter community, so Dave quit. 1 batch later, 19 years ago, I hired him to lead the complete virtual design with 2 Tier 1 auto engineering firms of something I'd invented 9 years earlier, an ultralight carbon fiber electrified hypercar like this 4 to 6 times more efficient midsize SUV. 7 years later, using methods we shared, Toyota designed a carbon fiber plug-in hybrid sedan that was 70% lighter than a same volume Prius. Carbon fiber electric cars entered mass production in 2013 with this profitable 124 mile per gallon equivalent model. And even with conventional materials, fleet vans like this 1-ton lighter aluminum hybrid we developed and road tested a decade ago could save 1/5 of US auto fuel and need no subsidy. But with carbon fiber structures, today's fastest manufacturing processes, like one we developed and sold into the supply chain that could make a complex 2x2 meter part in 1 minute, can now make carbon fiber electric cars at normal cost. How do we know that? Well, because BMW did it 6 years ago with this carbon fiber electric car that I drove for the last 2 years and will soon resume driving when the doubled range 2019 model arrives next month. The i3 reportedly made money from the first unit off the assembly line. Sandy Monroe, the normally understated dean of automotive costing, called it the most significant vehicle since the Model T and the most advanced vehicle on the planet. Validating our 1990s claims, its carbon fiber is paid for by needing fewer batteries, and fewer batteries mean faster recharging. The integrative design compounds saved weight far more than is usually assumed. The manufacturing is radically frugal and confirms the elimination of the conventional body and paint shops. It's also much better for workers. And overlooked synergies between ultralight materials and electric traction quadruple the efficiency without compromise and with many driver advantages. Making all cars this efficient could save more oil than Saudi Arabia lifts. Now, to make a car half to two-thirds lighter, you have to go repeatedly around the design spiral or design cycle. First, you make the auto light and slippery to cut its tractive load at least by half, and that permits smaller and more advanced powertrain and smaller chassis components, and that leaves more packaging space for comfort and more crush space for safety. But then you keep going around the spiral over and over because the less weight you have, the less weight you need. Many big parts then disappear. A good series hybrid can eliminate transmission, clutch, axles, differentials, drive shaft, U-joints, starter, alternator, flywheel, each saving even more mass. And at first, the special materials and powertrain and design may raise your manufacturing costs, but after more mass decompounding and simplification, you need so little carbon and powertrain, and the manufacturing, the advanced composite structures can get so much simpler that those two savings pay for the carbon fiber, making the ultralighting roughly free, as BMW just proved. Now, you must also organize the designers differently, and you must design in the future, not in the past. When the Soviet Union shot down Francis Gary Powers' U-2 spy plane in 1960, Kelly Johnson did not say, "I'm going to design a slightly better U-2. He said, "I want to own the skies for decades, so we'll design a Blackbird. I don't know how, but we'll figure out." And they did. It took him 13 months. Johnson understood that such an airplane was impossible within the conventional design context because he knew design was like a rubber band. If you try to stretch it too far from the conventional design space, you encounter more and more resistance, and eventually it breaks. But if you jump to the new design space you want to be in, you can stretch the rubber band back as far as needed for technologies not yet ripe, and as they mature, the rubber band relaxes to where you want to be. These auto examples also reveal a big policy lesson. With extra sticker price on the vertical axis and rated fuel efficiency on the horizontal axis, the official technology by technology analytic method, the underlying US and global efficiency policies, yielded the AQUA National Research Council 2001 high and low supply curves of potential US light truck and car efficiency about 15 years ahead, and then their dark blue 2015 updates catching up with previously rejected independent analyses. But within weeks of publications, these official forecasts were embarrassed by actual market platforms like these from Honda, from Toyota, a hybrid, from BMW, an electric vehicle, by major automakers, light metal, gasoline design, or gasoline engine virtual design in collaboration with our shop, and we could start mentioning that a decade later, and by a Porsche engineering virtual design using high-strength steel with a gasoline engine or with our estimate of a hybrid variant. In 2004, we also adapted the base vehicles in our winning the oil endgame analysis for the Pentagon based on our 2000 Revolution SUV design, yielding these typical light truck and car values. Now, NRC's component-based analysis, you notice, looking back at their original curves, misses the whole right-hand half to three-fourths of the design space. That is, highly integrative whole vehicle design can double to quadruple, and at lower cost, the fuel savings that policymakers now expect, but can't see in a technology by technology analysis. If you analyze efficiency potential by the part, not by the car, you'll think that efficiency is several-fold smaller and costlier than whole vehicle integrative design can actually do. So current efficiency standards are far more conservative than anyone thought. Electrification can be far cheaper and faster than today's heavy platforms are yet exploiting. That second shoe hasn't quite dropped yet. What about industry, which uses half the world's energy and electricity? Well, my team's latest $40-odd billion worth of industrial retrofit designs typically found 30 to 60% savings of energy, paying back in a few years, and in new builds, 40 to 90+% with generally lower capital costs. That's far better than the brown blob in the upper left corner, which is where most energy service companies deliver retrofits. Our better results come from thinking industrial processes and from redesigning basic elements like pump, fan, and motor systems. For example, in both buildings and industry, better pipe and duct designs can save about 80 or 90% of friction, and if everyone did it, this could save roughly half the world's coal-fired electricity, a fifth of total electricity, typically paying back in less than a year in industrial retrofits and instantly in new builds. Big numbers, and the methods are simple. Use big pipes and small pumps, not small pipes and big pumps, and lay out the pipes first, then the equipment. But such rearrangement of designers' metal furniture remains largely unnoticed and unpracticed because it's not a technology. It's a design method, and most people don't yet think of design as a scaling vector, ways to make things big and fast. In practically every building and factory, for example, a critical pump with an in-place spare pump is normally laid out like this, so flow always goes through two right-angle bends. That means friction. Why not lay it out like this so the main bend has no bends and also fewer valves? The same logic applies with identical pumps in tandem, a very common arrangement. So in California's Oakland Museum, our colleague Peter Rumsey retrofitted an efficient piping layout into the condenser water pumping loop, cutting the pumping energy by 3/4 with a 2 or 3 month payback, and eliminating 15 pumps that will never again waste energy and maintenance costs. When he also repiped the museum's chilled water loop and added variable frequency drives, he doubled the flow and saved 85% of the energy. To help the pipe fitters understand how to minimize friction, he simply asked them to lay out the supply pipes as if they were drains. Here's how most big buildings pipe cooling tower water back to the condenser. But if we lay it out instead as Peter does, everything gets better. The only obstacle is force of habit. We should bend minds, not pipes. What does such savings mean for the pumps and fans that use half the torque of the motors that use over half the world's electricity? Well, from the fuel burned at the power plant to the end use, there are so many compounding losses that only 1/10 of the fuel energy comes out the pipe as flow. But now turn those compounding losses around backwards from right to left into compounding savings, and every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and global weirding back at the power plant. And then as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. Now let's apply this logic to big data centers. 2/3 of the fuel fed into the power plant is lost in the plant and the grid. Half the metered electricity is then lost in the cooling system and uninterruptible power supplies, together half the facility's capital cost before even getting to the servers. Half the server energy doesn't reach the chips because it's lost in inefficient, usually very underloaded power supplies and in many, many fans to take that heat that largely shouldn't be there off the motherboard into the room where we can do dumb things with it. The next problem is severe underutilization of computing resources, partly through, or mostly through inefficient virtualization. Now the resulting energy flow, that little squib in the lower right corner, is about to vanish. So let's magnify it. The next thing is bloatware, running many unnecessary threads and processes and making simple tasks very complex because compute cycles were cheaper than programmers' attention and somebody else was paying for the energy. Downstream of all that, you may even have inefficient business processes. In all, a few 100,000ths of the original fuel energy actually delivers customer value. Where should we start fixing this? As usual, downstream. First, we write elegantly terse code, optimally compiled, with the goal that every compute cycle is a needed and wanted one. I had assumed this could save an order of magnitude in compute cycles, but recent tests suggest it's probably 2 orders of magnitude. And the shift to mobile devices now makes this valuable because it means battery time. Then we can at least quadruple the server efficiency, even more today, and then the servers will need far less cooling and power supply, both of which can also be done in much smarter ways. And we could even save half the utility losses by using fuel cell trigeneration, cheaper than the uninterruptible power supply it displaces. So multiply these savings from downstream to upstream, and you get at least 2 orders of magnitude, that is on the order of 100-fold energy savings. In the actual installation, by the way, the client wouldn't accept most of our recommendations, so we were only able to triple efficiency at the same capital cost. But our partner EDS said that had they all been adopted, we would have saved roughly 95% of the energy and half the capital cost. Integrative design can also transform energy supply technology. So RMI's SHINE team wrung out half of photovoltaics balance of system cost, enabling DOE's Sunshot program, and then joined with industry on 2 more rounds of whole system redesign. The latest 2x8 module solar packet or solar Lego block design is a highly integrated industrial product with 98% fewer parts, 10% less land use, all optimized for shipping, materials, civil works, electrical and mechanical installation, and wind loads. And this could unlock massive benefits across the value chain. Such a community scale, 10th to 1 megawatt roughly, ground mount PV system can match or beat wholesale prices without needing transmission lines. It can feed roughly 2.5 cents a kilowatt hour unsubsidized power straight into the distribution system. So what can integrative design do in a big economy? Well, 7 years ago, our business and design synthesis, Reinventing Fire, rigorously showed how to triple U.S. energy efficiency and quintuple renewables by 2050 using no oil, coal, or nuclear energy and 1/3 less natural gas, while saving $5 trillion, growing the economy 2.6-fold, strengthening national security, and cutting fossil carbon emissions 82 to 86%. Yet this would need, we found, no acts of Congress, no new inventions, but with smart city and state policies could be led by business for profit. We deliberately underplayed integrative design, which produced only 30% of the analyzed energy savings. The first 7 years of this 40-year journey are actually on track, green actual versus blue proposed, largely, I think, because the private sector smells the $5 trillion on the table. That's just what should be happening. Stimulated by those U.S. findings at the G20 2.5 years ago, the Energy Research Institute of China's National Development and Reform Commission published its roadmap for China's energy revolution, Reinventing Fire China, aided by Lawrence Berkeley National Lab, Energy Foundation China, and Rocky Mountain Institute. It details how China can save $3 trillion, run a 7-fold bigger economy in 2050 than 2010 while using today's energy 7 times more productively, emit 42% less carbon, burn 80% less coal, and get 13 times more GDP from each unit of fossil carbon. This roadmap strongly informed the 13th 5-year plan, whose energy authors were our steering committee. So extrapolating these on-track U.S. findings, adopted Chinese findings, and similar European ones to the other half of the world could get us to about a 2-degree climate trajectory while providing the same or better energy services, roughly $18 trillion cheaper. Then reinvesting part of that saving in natural systems carbon removal could reach the Paris Agreement's aspirational 1.5-degree target, still with trillions left over, plus many of the UN Sustainable Development Goals achieved. So energy efficiency through integrative design can help make climate protection not costly but profitable, and that should simplify the politics. Vanishing demand is going to severely stress the car and hydrocarbon and electricity industries. And their managers understandably focus on the need for price to exceed cost. But the other half of the business condition needs value to exceed price. Because if competitors offer a superior value proposition and run off with your revenues, it doesn't matter if you can profitably sell what your ex-customers are no longer buying. When that value proposition shifts, markets can flip with breathtaking speed. On New York's Fifth Avenue in 1900, you have to look hard for the first car. 13 years later, you have to look even harder for the last horse. The non-farm horse market peaked in 1910 when there were just 3% as many cars as horses. The horse and buggy industry thought it would have decades to adapt, but Ford's Model T got 62% cheaper in 13 years. Car-owning households soared from 8 to at least 60% in a decade to 1928, 3/4 financed by GM and DuPont financial innovation called car loans. Well, today, PV modules just got 80% cheaper in 5 years. 3/4 of our rooftop solar is innovatively financed, and Ford's and Edison's industries are joining together to eat Rockefeller's industry. So, as these photos show, the pace of transformation is set not by incumbents, but by insurgents who are not inhibited by incumbents' business models or legacy assets or cultures. Moreover, investors flee before customers do because capital markets keenly sniff out disruption. And once they think you're in or even headed for the toaster, they don't wait for the toast to get done before they decapitalize you and invest in your successors. Already $6 trillion have prudently fled the fossil fuel industries. Carbon Tracker's investment analyst Kingsmill Bond uses examples like these to illustrate that brutal market logic. He says, any fast-growing challenger will rapidly take all the growth in a slow-growing market. As a rule of thumb, he says, incumbent sales will peak when the challenger gets to about 3% market share. Why is that? Well, because most investors seek growth, not mere size, and they try to sell out just before sales peak, because after that, stagnation strands assets while competition drops prices. So Bond concludes, renewables are fast-growing, disruptive technologies that have reached critical mass and are transforming the global energy system. Investors in incumbent energy companies are at risk. Well, yes, smart investors agree that renewables will squeeze out fossil fuel generation's remaining growth within a few years. But for the same reason, global auto shares have been underperforming since 2014 as electric cars emerged. This game-changing dynamic is what matters, not insurgents' initially small market share. That is, modular, scalable, mass-producible challengers in supply and now in efficient use can combine rapid growth with increasing returns. And those two attributes can create a surging swarm of smart, agile mammals that quickly displace the big, slow-moving dinosaurs. Here's the relative share price performance of one new and two old automakers. A 2003 startup called Tesla Motors surpassed Ford's and for a time GM's market cap while selling 2 or 3% as many cars. And now electric cars with just 2% US market share are seen as the inevitable successor, while incumbent automakers like electric utilities, like giant oil companies, are struggling to reinvent themselves. I hope these examples from the demand side will encourage you to enable the new energy system, not protect the old. So the global energy transformation can move at the pace and cost of design and of software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents. I'm glad we have so many insurgents here today. And I thank you all for your good work and your kind attention.